Okay, good afternoon. I'm Tianhao Liao, and here in the Electrical Engineering Department. And I would like to share some of my work I did before and later some recent study. So it's mostly about the application using the radar remote sensing. Okay, and you see the affiliation. Here we have a new center, research center on campus, focused on this new communication and the remote sensing technology. So most of faculty here are supporting this center. Okay, so some my background, that what I have been done for the radar polarimetry when I was in my PhD and the postdoc. And first part of my postdoc at the University of Michigan, and basically I did the rough surface scattering. So we have the 3D numerical Maxwell model, and apply this to simulate a rough surface at the LCX band. So it's important because when you talk about scattering, you always have a surface. Either you shine the surface or something bounces the object and to the surface and coming back. So it's important in estimating the scattering rough surface. And of course, agriculture is a very popular topic. So vegetative surface is the main subject because a lot of places on the earth are covered by vegetation like a forest, grassland, and also your agricultural field. And this will link to the later the soil moisture study using this model, because the soil moisture will relate it to how much water you irrigate for your agricultural field. So the mission I was involved, NASA's MAP mission, soil moisture active passive. Basically, they want to estimate the soil moisture to give some suggestion for the community, like the farmers, or like the government, they can have some policy on that. So later part of my study when I was postdoc at the JPL, Caltech, and that time I was doing the radar interferometry over the wetland at the lower Louisiana. So that part we use INSAR to estimate the water level difference. And they are very interested in the change of a wetland because the mangrove along the wetland, the vegetation is retrieving and shrinking. They want to use the INSAR to know how much the dynamics in the wetland. Okay. So the radar polarimetry part. So this is a very popular topic because right now the Earth observation satellite, there are many of them, and actually this year is a very good year. We have the ALOS-4 data finally released. So, and the NISAR, the NASA-ISRO joint mission for the L-band SAR launched 2 weeks ago. And the L-band coming, there is also the ROSE-L and the tandem L. So L-band, the wavelength is about 25 centimeter. So it's around the size when you talk about the vegetation geometry. So it's very important to study the scattering phenomenon of around this wavelength. So that's a very popular frequency for the Earth's observation. And also going to the higher frequency with a shorter wavelength, C-band and X-band also popular. But the X-band is, a lot of time the X-band is more popular for mapping the DEM, so to create a very fine resolution of the DEM. And the C-band kind of in between, so the wavelength is like a 5 centimeters. So the typical model will kind of to separate the application depending on the canopy height for these three frequencies. So what is the scattering? So this is a simple drawing to show the rough surface scattering. when we talk about the radar, so it means you have the sensor to shine a wave down to the scatterer. And the scatterer will create, after the shining, it will create a lot of scattering in every direction. And usually your satellite will shine the wave and receive the wave at the same place. So it's called the backscattering. However, the scattering actually go into many directions. You just don't receive them. So what we simulate here is to consider a rough surface and discretize it and simulate using the Maxwell equation and to get the backscattering. That's how we get this result, how we set up this environment. So there are many methods to do that, but if you base on the Maxwell equation, here we use we call the method of moment to do the numerical simulation. But first you need to formulate the problem. This is a dielectric problem. That means this pointer is not that good. So you have a rough surface here, and the air has a permittivity, and also your soil has permittivity. So when the wave shines to that, some of the wave penetrates, some of scattering. So it's a problem of a dielectric medium problem. So you have some governing equation to link your incident wave and your discretized surface. And the purpose is to find out the induced current along the surface. Then you can use this surface current to radiate back. Then that's your scattering. And at the back scattering direction, you get the value. That's how you do this kind of problem. So when you increase the size of the surface, let's say the 8 meter by 8 meter, depending on your frequency you want to solve, every wavelength at least you need like 10 discretization. So you can easily expect that if you increase the surface size, the unknown will increase dramatically. If you are doing this 3D problem, at one point you will need some algorithm to speed up your calculation. Otherwise, you'll end up with a very large matrix with like a sparse matrix problem. So there is acceleration applied to this called basically we depending on the distance to the grid you are talking about. You can consider there's a strong interaction or a medium interaction or a very weak interaction. Based on different strengths of interaction, you can apply different acceleration algorithm. Okay, so then you will simulate the result, and here we get the backscattering, coherent scattering, incoherent bistatic scattering. And you can see here, our shining angle is 40 degrees. So the geometry is here, your shining angle, this theta I, and the theta S is your scattering angle. The plot here, horizontal axis is your scattering angle. So your backscattering is your minus 40 degrees. It's very small. But your forward scattering, just like the mirror, when you have a mirror, the largest reflection is in your specular direction. It's very strong. So this is a kind of problem you are solving a very small value. So the accuracy can fluctuate quickly. So it's a very difficult problem to check the accuracy. But if you talk about the forward scattering, which is very big, so you can easily get the value at the ballpark. So that's why recently the mission about GNSS, they actually take advantage of this. You have so many GPS L-band signal already there. Every time they shy away because they need to get the position. Then we just need to set up a receiver everywhere to receive this forward scattering, strong power. And we just figure out the phase or the location. There are a lot of applications coming out. So, but my point is that if you have only one satellite, you are doing this kind of problem, backscattering with a small value. So in the past, we simulate this rough surface using the parallel, this supercomputer, but this is a long time ago, just to show the old days. This one is stamped in Texas. Yeah, okay, so this is a basic for the 1 unit, but it's very outdated. So then for your remote sensing, you have to define we call the polarization. So there are vertical and horizontal polarization. So here I just show some result from this study. So this we validate our backscattering result at a different looking angle. So this the L-band result. So during the 90s, there are the measurement data from U of Michigan. They have the multi-angle and the multiple frequency, which I will show later, over 20 to 50 degrees. So we validate our model with this multi-angles backscatter. So VV, HH, and the cross pole. Ideal cross pole should be identical between HV and VH, but when you take a real edge measurement, there will be some difference. So we take like an average of these two to do the comparison. So actually, we also put some analytical method here. I think here the numerical Maxwell method shows the best agreement. And the interesting thing to mention to Professor here, the Professor Magadan's group, they were doing the EBCM method. So around that time, they also verify their result with this MM3D for rough surface scattering. So then we also do the validation for C-band. Okay, you can see here the copole follows pretty well. And the cross pole, the Maxwell equation get closer than the analytical method, which is a little bit underestimate the value. And also the X-band. So we verify these three LCX for multi-angles. Okay, so the second part then about the vegetative surface. So this study was initiated because of SMAP mission. And they want to estimate the top 5 centimeter soil moisture for this vegetated land, including the 4 major crops: soybean, wheat, corn, and okay, sorry, it's a grassland. So grassland is not the crop. But later also they include the canola. So there is a field campaign to validate the mission's product, so which happens during summer of 2012. Okay, so the vegetative surface model in the last few decades, the distorted bone, which is based on the single scattering incoherent model, was very popular because it's very straightforward to understand the mechanism. So we have here the vegetative surface. We separate into 3 parts to explain the 3 mechanisms. First one is called the volume scattering. So the wave just bouncing the vegetation and going back. And the second one is a double bounce. So that means it bounces the vegetation, also the surface, and go back to backscattering. So there are 2 identical paths, just in different direction. So which we highlight here. If you do the reverse way, it should also be the same path. And the third one is the surface scattering. So the wave just passed through the vegetation, bouncing the surface and coming back. So these 3 mechanisms in the past, we just calculate individually for the scattering of each other and add them up incoherently. So you can already see I emphasize the incoherence. So it's very straightforward, but it's not that realistic because you know the scatterer, they will have an interaction. So coherent effect was not considered in the past. But it was a pretty good model to estimate soil moisture for quite a long time. And if you are familiar with field interference, then you will see here I put a 4. Because these two similar paths, it will give you the same field. When you add up the two in-phase field and take the square of the power, you actually get the factor of 4. So this is a very interesting factor to include. It's called the backscattering enhancement, including the constructive interference. So based on this one, we have a clear separation of 3 mechanisms. And this also becomes the basis of the decomposition, polarimetry decomposition, because you can know each contribution and set up the basic function for the decomposition. So then, how do we come up the scattering? We use the simple cylinder and a disc to construct the vegetation. But the vegetation for the grass, we use just a cylinder, but grass can be oriented any direction. So the orientation becomes the key to describe if you consider among different crops. So for the wheat, we also use only cylinder, but the wheat is mostly vertical. So it comes with only light orientation. But for the soybean and the corn, you cannot just use a cylinder because apparently there are leaves. So analytically, we include a disc to model the leaves. And also for corn, at that time we just use a disc instead of considering those bending structure of the leaves. So try to catch up the main scattering effect from the stalk and the leaves using a simple geometry. But as I mentioned, the key will be how do you distribute those targets. So for grass, it can orient any direction, but for corn and the wheat, the stalk can only vary a little bit. So this makes a difference when you consider different crops in the geometry. So first, I would like to show some this simple geometry validation with existing the HFSS and FACO. So which is a very popular commercial software in solving electromagnetic problem. Okay. So this is a general view of let me skip this one and come back. Okay, so here there is a cylinder, and we have 3 methods here. The analytical method is infinite cylinder approximation. And we have HFSS and the FACO result. It jumped. Okay. And this is a bistatic scattering. And the red dot is the forward scattering, double bounce direction. We can see actually the commercial software method agree very well for these two based on different algorithms. And for analytical method, for left-hand side, this is a shorter cylinder with about 40 centimeter long. And there is some difference, but the trend follows for both the VV and HH. As we enlarge the cylinder to 2 meters, the comparison are very well among these 3. So in the past, we used this ICA to simulate the cylinder. So later now we confirm this with commercial software. So for the single cylinder, actually it's pretty fine to use the analytical model to do that. Similarly for the disk, we have an infinite disk approximation, an analytical solution. So this bistatic comparison for left-hand side the smaller disk, and right-hand side the larger disk with larger radius. Actually, they compare also pretty well. So this single cylinder and single disk is the basis for us to construct all these different kind of vegetation in the past. So the incoherent model says that if we decompose this real geometry into like one cylinder with n disk, saying that these leaves are modeled with disk, they just scatter individually and we sum up their power. So they don't have the mutual interaction. So that's an incoherent model, which has been used for a long time. At the end, we'll mention some in progress to do the full wave. So this page is to show you have this schedule, then you have to consider how much angle they bend. So these are the distribution of the orientation. And the nature is very complicated. You don't know exactly how the vegetation orient. You just know they have some distribution. So there are the average over the distribution angular range to be considered. So this is an analytical way to consider this distribution. Okay, so in the past when we do the corn, I just highlight this. This is a step further based on the single scattering model. So if we have a single scattering, then we can consider if we know we can just extend the number of scattering to second order, third order, or even more. So this one will show an example. Left-hand side is a double bounce. You have bouncing the object, surface back, or reverse. And if you want to consider the second order scattering, that means you have to bounce the object twice. So by counting this, like this this kind of a drawing, counting the paths, you actually can count how many kind of combinations you can come up this second order scattering. Then we just sum up all these scattering power and to get our multiple scattering effect based on this power scattering. So then there's a different way to find out all these combinations. So this becomes just like a mathematical problem. First you count how many combinations. Then based on this scattering, you can multiply the corresponding reflectivity or corresponding scattering of the object. Then you can get the sum of all this scattering power based on different mechanism. And because this return path will be exactly the same path, so the scattering field is the same because of reciprocity. So we always have this backscattering enhancement. Okay, so here shows a result that the improvement for the multiple scattering affect quite a lot for VV if you consider the higher order, which will accumulate more higher order scattering power. So the red one for VV, red solid line for multiple scattering, red dashed line for VV, just single scattering. Okay, so important part of this is to validate with measurement data. So during we call the field campaign, usually at the ground, we measure the moisture, soil moisture, and the vegetation structure, and the vegetation water content, like a biomass. And in the sky, we fly the airborne sensor, L-band sensor. So because soil moisture vary a lot, so we have to fly the sensor at the same day you take the soil moisture. But the vegetation grows slower compared to the soil moisture change. So every week we'll take a vegetation measurement. So this lasts about 6 weeks. Then you can get a certain amount of field campaign data. Maybe you have like a 12 acquisition from the radar. then it will be enough to establish a growing cycle of the vegetation to study that. Okay, so these are just a validation. And also the structure is important because this is related to how fast it grows. So we take the measurement of a radius, stalk length, and correlate that to the vegetation water content. Because you know, as you grow larger, you contain more water. So the water content will be the good variable to link all the parameters regarding the vegetation. And the model can be complicated. Even it's a simple model, you need to run the model. So usually we provide this called the data cube for the real application. So it captures 3 important axes. So this just shows the VV and HH in dB. So the vegetation water content is one axis, and the surface roughness and the soil moisture, which is the soil dielectric, are the third axis. Based on the variation of these 3 axes, we create the corresponding VV and the HH data cube. And this will be helpful later use this data cube to retrieve the soil moisture back, which is retrieve the soil permittivity, then the soil moisture. Okay, so this is the time series algorithm we applied. Basically, you try to minimize the difference between the observed backscatter and your data cube to locate the close parameter set. But there are some assumptions you can apply, like vegetation water content doesn't change that much. So there is some criterion constraint you can apply in this study. Okay, so this is just the side-by-side comparison, which we have pretty good agreement. And this is a retrieval of soil moisture. So the dot is the measurement, and the line is the prediction. So for many sites, we have a pretty good under the 0.0, around the 0.02, which usually we consider like under the 0.06, the RMSE is good for the soil moisture retrieval. So we have some sites lower to the 0.02, and overall around 0.06 here. Okay, so the second half is my radar interferometry. I apply this to infer the water level change. So this L-band sensor, I mentioned this earlier, let's skip. So this L-band application, the NISA, which is just launched, basically focus on a lot of disaster prediction and estimation. And among this, there's a wetland study to know the retreat of this mangrove size. This marsh around the lower Louisiana. So there are many in-situ measurement sites set up like this to measure the moisture and also other sensors about the vegetation species. So what I use are mostly the red dot side, which we have the swamp with some trees in the water, and the lower part, the yellow dot, are the marsh sites. So I use the ALOS pulsar data, which was active between 2007 to 11. So around here, the baseline is 46 days, but they have a regular acquisition, which is good. So overall, we have 25 pulsar data, and the INSAR pair with 40 to 60 days, we have 17. And the physics behind that is like this graph. This INSAR, you need 2 acquisition of an image, and you want to find out the difference of the phase. So the phase is related to your path length. So when you have the water level lower, you get one image. And when the water level is higher, you get shorter path. So these two, if it's the same pixel, so the only difference is the path length. So this difference will reflect on the phase difference. So we just find out the phase difference and relate to the wavelengths, and we can know how much difference between the water level. So this is also called the differential INSAR. But since the phase you are familiar, you only have a 0 to 2 pi, right? But your water level difference can be larger than, can be many wavelengths. So there is some issue when you do the processing. There is a phase unwrapping part you have to deal with to find out the real phase, not the wrapped phase. So this is a basic flow. You have a two SAR image, single look complex image coming in, and you form the interferogram, and you estimate the coherence. And you have to remove topography, do some filtering, then you get a phase difference, right? But this phase difference you need to unwrap it. Then you use that unwrapped phase to do your science study. So first, we have two products important here. First is the coherence. Coherence shows that how much your signal correlate when you take these two images. When you have a higher coherence, then that's your phase estimation is more reliable. And if you have a low coherence, you have to be consider whether they are not, it's good to use those phase to infer your water level. But on the other hand, this phase coherence also an indicator about how much dynamics in your study field. If your vegetation change a lot, that means it's not that similar to previous one, then you can expect there are a lot of decorrelation. So this has like a seasonal dependence. You can see during the summertime, you get some lower coherence because the leaf increase. And in the winter, not much change, so you get higher coherence, which is brighter. Okay, so then also this can verify with we call the normalized difference vegetation index from the optical sensor to show this greenness change of a vegetation. Okay, so about the interferogram, I use the HH polarization to create the interferogram. Before you do the unwrapped phase, you may expect like this kind of pattern. You see the repeated color wrapping. So that means it already experienced the 2 pi from this cyan color to red and to cyan, and already 2 pi, but your phase is more than that, so it go back to repeat it. So you see this repeated pattern. So this initial interferogram, we have to unwrap it. Okay, so let me see. So after we unwrap the phase, we can use a formula I presented earlier to convert it to vertical water level change. So this is the final map for those interferogram. And we can see the color here corresponding to this color bar. You can have the positive water level change, which will have water level increase, or water level decrease with the red. Okay, so this very good way to estimate a larger domain variance of the phase difference, which is there is even more better example about the subsidence. Subsidence usually at a millimeter level, and it's very difficult to use in situ measurement to measure small change. But with remote sensing data like this, you can easily see a the complete area change of with a significant amount, which you cannot hide from the radar in this kind of observation. Okay, so we just have a side-by-side comparison. Around that time, I got a very good coherence and retrieval for swamp, which we have a strong I think the double bounce from this trunk trees inside the swamp. But the correlation, the estimation, I didn't have much correlation for the marsh. So I think for the study of water level change around the marsh is still left to study. So maybe there are more correction on the phase we need to perform before we go to the retrieval. Okay, so finally I have just a quick few slides about my recent presentation at the IGAS for our recent progress. So this graph, right-hand side, I just used some time earlier to describe as a path model since 90s. But you have those scatter, just scatter within this layer. We don't really have the plant concept because we use a single scatter to calculate scattering. But what in our mind is a plant, like the real plant, and you put many of them in the field. So we want to simulate the real plant scattering and combine with the surface instead of doing the single part of scatter and just uniformly distribute in a layer. So the method we use is called the multiple scattering theory. So the idea is that once you can calculate the accurate scattering of one single plant, this can be done with commercial software because the geometry can vary a lot. We don't need to just focus on this part. So assuming we calculate the scattering of this one, we can use we call the T-matrix method. T-matrix is converting your exciting field to scattering field. Then if we know the T-matrix of this single scatterer, then the multiple scattering scheme is like the bottom two figures. If you are considering the scattering exciting field of the single cone plant, the scattering comes from all other scatterers, including the surface. And if you considering the surface as the subject, its exciting field comes from all the other scatterers, including the incident field. So based on these two concepts, you can actually formulate a multiple scattering scheme. And each of them, each of scatter, including the rough surface, they are represented by the T-matrix. So all these scatterers are interact with the T-matrix. You just need to formulate how many contributions from others to yourself. So you cannot scatter to yourself. So multiple scattering, when you consider the subject, it does not include the scattering of itself, but all the others. So then let's revisit this formula. In the past, incoherent model, you do cylinder disk individually and you scatter the power and the sum of them. So now they do not have an interaction. But now you do the scattering of the entire plant, even you use just cylinder and disk. You can use the commercial software, get the scattering power by static of this. Then you have a single plant by static result. Then you can incorporate this into this T-matrix calculation. I skip many details. The calculation of a T-matrix I haven't mentioned, and how to interact with them I didn't mention. But the idea is that based on this, you can formulate a large problem of a large domain. Okay, so let me jump to the quick result. We have an initial result with 8 cone plant over the rough surface. And these two are the graph I showed earlier, if you put in equation. And this is a comparison of this method, fast hybrid multiple scattering method with a FACO. FACO commercial software, you put the 8 cone plan along this rough surface and calculate the scattering power. And we show this compared to agree pretty well. For the scattering power, just right behind the cone plan. So just in between the surface and cone plan. And if you look at the VV and HV, which will shine the V pole at this comparison, they also compare pretty well. Okay, so that's my talk sometime. So this is my recent selected publication on this remote sensing study. And thank you very much.